Hey, Mr. J here with a proof and a theorem, one of my most favorite proofs of the year. And so I thought it was worthy of a video. And because it's a bit complicated, a bit abstract, and might require you to watch it more than once. The other part of it is that this is a great example of where proofs make things more understandable, that it kind of explains things because it breaks everything down into little pieces. So it might not be understandable up front, but in the end, I hope you do. And I compare this often to driving a car, right? And that we're going to be the mechanic today and get under the hood and understand why it works. Okay, so let's jump into the angle bisector theorem today. And we'll go over to Chrome because I'm going to do this on GeoGebra. And I hope you guys will reach out if you have any questions. And so here's our triangle. And I hope you can see how this is an angle bisector. BD is a bisector of angle ABC. And what it does is it creates proportionality. Do you see how BA is to AD? So this side, BA or AB, however you want to call it, I have it labeled as BA, is to this segment or this part of AC, which is created by AD because of that intersection with the angle bisector. So this is to this. Grab a pen here. This is to this as this is to this. BA is to AD, ratio 2.65, as CB is to DC, as this piece is to this piece. So we have proportionality. Now the thing that's surprising, the thing I like about this is that it's not obvious why we would have that. I hope you see that these triangles are not similar. So we look at triangle, oh, excuse me. If we have triangle BDA, it's one triangle, and another triangle, let's make it say red, BCD. Those are not similar triangles. The angles are not congruent. I hope you see that they are different shapes. But we still have proportionality. So we have proportionality without similarity. Right? Is it clear that we have proportionality without similarity? I know if we have similarity, we always have proportionality. But I think it's surprising that we have proportionality in this triangle, in these two triangles, and they are not similar. At least you don't see the similarity. There's actually an extra triangle that is not apparent. It's actually hidden, working in the background. And so I'm going to show you that. And that's going to be the justification for the proportionality. So to do that, let's go and bring in some lines. I'm first going to extend line AB. Okay, there's AB, an extension, the black one there. And now I'm going to bring in this line, and a little hard to see. How did I draw that? I hope you can see that I drew this extension by just making AB longer. That's how I drew AE. But how did I draw CE? What is true about CE? Do you see how it was drawn? Well, what's happened is I took this line here and I drew a parallel line to it through point C. So that's an auxiliary line, we call that, a helping line, okay? And so these are parallel. And there's a reason we did that. We did that in order to create the two triangles that are actually similar. And let's see if you see the triangles now. I'm going to draw them in for you. Okay. One triangle is triangle A, B, D. Can you see that triangle? Okay. The other triangle is A, E, C. And we'll finish that. And those triangles are similar. This is called our side splitter theorem, where this top red triangle and the blue triangle have a reflexive angle here, and there's a corresponding angle here. And so they are proportional. And let's talk about which sides are proportional. Do you see BA is to AD? Right? The left side is to the right side of the small triangle, as this here, BE is to DC. So we don't have CB. I don't know what that's for. We'll get back to that in a second. We have BE is to DC, right? So this is to this as this is to this. And that's called the side splitter theorem that we've talked about. So that's proportional. So the question is CB really congruent to BE? I've got too much ink out there now. Is this piece here, or this length right there, congruent to this length right here? And if that's the case, then we could substitute. And there would be our proof. And I'll tell you why we can. We can definitely substitute. So let's go back. This was one angle that's bisected and therefore congruent to this. Because we drew an angle bisector, do you agree that these two angles are congruent? Can we also say that this angle is congruent to this angle because of corresponding angles? And this angle is congruent to this angle because of alternate interior angles. We have this transversal of parallel lines, which means this angle and this angle are congruent. What does that do for us? Doesn't that create isosceles triangles? Isn't this now congruent to this because we proved this angle is congruent to that angle? And therefore, we can substitute CB in for BE. There's the CB now. It was BE. I hope you saw why BE was okay to be proportional. And now we can just substitute it in. And there's our proof. And so, in summary, let's talk about what's happening. You know, we do not see these lines when we're doing this, right? We see the angle bisector and we think it's proportional. The reason it's proportional is because there's really always an isosceles triangle created by these auxiliary lines down here. There's always this isosceles triangle down here, right? And so this length, this length of BE is always congruent to CB. And so we always have this proportionality. I think it's a cool theorem. I think it's an interesting one. The question now is, can you write a two-column proof that would detail all of these steps? And we will get to that. I want to see if you can do it now that you understand it. Remember, whenever we're writing theorems, we need to understand the concept first, and then we work from the top down, from the givens down, and also from what you're trying to prove up. Okay, thanks. Have a good day. See if I can close this out.